Hello everyone, I'm Chris Choy from Nvidia Research. I would like to first thank the organizers for inviting me to this robotics workshop. Today, I will present one of the most important representations for 3D perception, the sparse tensor, and what we can do with sparse tensors in 3D perception. Before we proceed, I would like to briefly discuss why we cannot use a standard tensor that has been widely used in 2D image processing for 3D perception. First, a typical 2D image consists of a dense grid of numbers, and if you zoom in, you will see non-zero values almost everywhere. However, in 3D or even high-dimensional spaces, the majority of the space is empty. Here, we have a 3D scan of a room, and the space of the beds is empty. If we represent it as a grid, the empty space will be represented as zeros. This ratio of empty space or zero values increases as we increase the resolution of the space since the volume increases cubically while the data or the surface increases quadratically. If we use 20 centimeters for the voxel size, the 78% of the space is empty. But as we increase the resolution up to 2.5 centimeter voxel, 98% of the space is empty. Thus, if we apply any operators on this dense tensor, 98% of the computations will be wasted on the empty space. Instead, we can only save the non-zero values in the grid like a sparse matrix, but in a high-dimensional space. This gives a sparse tensor, and we can think of a sparse tensor as an n-dimensional extension of a sparse matrix. For example, if we stack sparse matrices along a new axis, then we have a high-dimensional counterpart, and this becomes an unordered 3 sparse tensor. These sparse tensors can be represented as a set of non-zero values and associated coordinates. This representation is known as the high-dimensional coordinate list, or high CO representation. Then let's compare some pros and cons of the point cloud and sparse tensor for 3D representation. The first thing to note is that the point cloud is usually continuous, whereas a sparse tensor uses discrete coordinates. So point clouds do not incur any quantization error. However, there is no bound on the number of neighbors, and random access is not possible. These make it difficult to use the point cloud for scalable training. Also, hierarchy is not defined, or we have to use a heuristic sampling method to create a hierarchy. On the other hand, a sparse tensor incurs quantization error, but as we can represent high-resolution 3D scans efficiently, usually the quantization error is negligible. Also, there's a bound on the number of neighbors, and random access is possible using a data structure like a hash table. Lastly, the hierarchy is deterministic and straightforward. This hierarchy is one of the crucial components made a CONVNet so successful in image perception. So in today's talk, I will first go over how we can implement this convolution on a sparse tensor efficiently and applications such as segmentation, representation learning, registration, and detection using a sparse tensor. First, let's talk about convolution and sparse tensors. You may wonder why we care so much about convolution in 3D data. 3D data is not 2D images, they're different. But let's think of where the images come from. They're merely projections of our 3D world, and if convolution works for the distorted version of the original data, then convolution on the original undistorted 3D real world should work really well. Secondly, the convolution is the most general translation invariant operator, and it is why it can be used for a perception system which should work in anywhere in the world, regardless of the longitude, latitude, and altitude. Also, a convolutional neural network has been known to capture the best inductive bias and regularization for 2D perception. It is also very effective at creating hierarchical feature maps that increase the receptive field sizes multiplicatively. Last but not least, we have vast prior research, heuristic architectures, as well as open source libraries and expertise that would allow us to transfer our knowledge from 2D images to higher dimensional convolutional neural networks. In this slide, I'm going to compare some of the most common neural network operators used for 3D perception. First, we have the conventional dense convolution. We have directional weights for different offsets, but representing a 3D space is inefficient and computationally expensive. Next, we have an MLP, or a point net. It simply is a matrix multiplication, and you can think of it as a convolution with kernel size 1. Thus, it does not support directional weights. The next operator is a graph convolution. It is similar to an MLP in that it does not support directional weights, but instead it aggregates features from neighbors. So it is technically not a convolution. Continuous convolution is similar to the dense convolution, but searching neighbors in a continuous space can be slow, and also representing a continuous kernel incurs some amount of approximation, which results in lower accuracy. Lastly, we have convolution on a sparse tensor, or sparse convolution. It is similar to both dense convolution and continuous convolution, except that we have discretized the directional weights as well as the coordinates for computational efficiency. This is the best combination of efficiency and expressive power. This is a simple visualization of a dense convolution. First, it takes a small section of the input and computes a weighted sum. Similarly, on a sparse tensor, these operations are applied only for non-zero values, but essentially the convolution operator is the same. Let's discuss how we can implement this convolution. On a dense tensor, we compute a convolution first by converting an input feature map into a matrix by applying an operation known as IM2col. Similarly, in a sparse tensor, we create an intermediate feature matrix by reorganizing features using what we call the kernel map. Once we reorganize features, the convolution is simply the sum of all matrix multiplication outputs. Specifically, this kernel map defines which input features should be mapped to which output features and can be represented as a pair of row indices in the input and output coordinates. Let's say we have 3 non-zero elements in the input coordinates at the bottom and 4 non-zero elements at the top for the output coordinates. If we apply 3x3 convolution, the first input coordinate will be mapped to the 0th coordinate of the output through the kernel index p. Similarly, the 0th input coordinate will be mapped to the 0th coordinate of the output through the kernel index I. We continue this process to find all kernel maps for all coordinates. Then we are left with these 3 kernel maps. Except for the kernel index b, h, and I, we do not have valid kernel maps for the rest of them. Given the kernel maps, the convolution boils down to a series of matrix multiplications. First, we use the kernel map input indices to create a gathered input feature matrix. Next, we compute the matrix multiplication between the features and the weights to create the output features. Finally, we scatter the output features to the correct position using the kernel map. Finally, we repeat this process for other kernel indices. In MINKOWSKI engine, the library that we built for building neural networks on a sparse tensor, all these operations are implemented and accelerated through Nvidia GPUs. Now that we learned how a convolution can be implemented for a sparse tensor, let's delve into how we can implement this idea of MINKOWSKI engine. First, we have to understand how mini-batch can be implemented on a sparse tensor. In 2D images, we create a mini batch with a dense 4-dimensional tensor, and the 0th dimension is the batch dimension. Similarly, we use the batch dimension for the first dimension of the coordinate. For example, if we have a 2x4 matrix like this, we can extract non-zero coordinate and associated features like this. Here, 0th row and 2nd column of this matrix has value 2.1. And that's what we have on the coordinate and feature matrix respectively. Now, we add zeros to the coordinates since this is the 0th batch of the data. If we have more than one batch, we can use as many batch indices as we want. Next, given the batch the coordinates, let's create a sparse tensor on the MINKOWSKI engine. First, you can simply pip install MINKOWSKI engine, or you can use the latest version with this command. Then, you can create a sparse tensor by simply feeding the features and coordinates to the sparse tensor class, or you can use the MINKOWSKI engine utility function to create the batched coordinates. If you want to use the Nvidia GPU acceleration, provide the GPU device argument like this. And creating a layer is also very simple as creating a network in PyTorch. Simply add a list of layers you want into the PyTorch sequential. And here I added convolution, batch normalization, and ReLU layers. And feed forward is just simply passing the input sparse tensor as an argument to the layer. Now that we discussed how we can build a convolutional neural network on a sparse tensor, let's discuss some applications that we can solve using a sparse tensor. The first topic is 3D or 4D spatio-temporal semantic segmentation. 3D semantic segmentation is a problem pertaining to partitioning 3D scans or data into semantic parts. And similar to 2D semantic segmentation, we can solve this problem by labeling each voxel or point in the 3D scan as one of the predefined semantic labels. Here I visualize the 3D input point cloud on the left-hand side and the network prediction on the right-hand side. To get such predictions, we proposed 3D fully convolutional neural networks on sparse tensors. In our CBPR 90 MINKOWSKI paper, we proposed the first very deep convolutional neural networks for 3D semantic segmentation. Specifically, on our CBPR 19 submission, we achieved the best result on the SCANNET benchmark with a convex which consists of 42 convolution layers. At the time, the deepest 3D convex only had about 12 layers. So compared to that, our network was very deep thanks to the efficient representation and computation of sparse tensors. Also, since we're learning convnets, which have been widely studied in the 2D domain, we are able to reuse many of the popular network architectures, such as ResNet and UNets. Here, we visualize the network architecture of ResNet 18 and our high-dimensional counterpart. Also, here's a typical network architecture that we use for this task. Although we use 3D cubes to represent each block, all tensors in this network are sparse tensors. Here's a typical prediction of our network. On the top, you can see the input, the network prediction, and on the bottom, we visualize the difference between the ground truth and the prediction. Note that except for very few regions, our network was able to predict the semantic labels very accurately. Here's another prediction visualization of a SCANNET kitchen scene. On the bottom right, you can see the difference between the ground truth and the prediction, and can see that the network predicted a refrigerator as furniture, but the ground truth label was door. So it makes sense that the network got confused. And all these network predictions are generated from a fully convolutional neural network. So we do not have to crop regions to extract features. So like fully convolutional predictions into the images, we simply feed the entire scene to the network to get these predictions.
Quantitatively, we were able to achieve a large performance jump on the standard SCANNET 3D semantic segmentation benchmark. Compared with the previous year's state-of-the-art methods, point CNN and 3D multiview, which uses additional image features to the 3D point cloud semantic segmentation to boost the performance, our method was able to achieve almost a 20% MIOU improvement in a single year with only the point cloud input. And it is still one of the top ranking algorithms on the benchmark. However, in many interesting problems in robotics require identifying dynamic objects. For example, in this video, we have a sequence of 3D scans, and cars and pedestrians are not static. This creates a 4D spatio-temporal continuum, and most of the interesting problems take place in this four-dimensional space. So in this work, we extend the 3D convolutional neural networks to perception in four-dimensional space-time. Also, there are many advantages of using such 4D data for perception. One of the first advantages is that there are temporal consistency constraints that can limit the possible outcomes. For example, if we observe a steady object at multiple time steps, all class label predictions have to be the same. Second, it can sometimes provide novel viewpoints that reveals some previously occluded parts. Lastly, we can observe actions or dynamics of an object or interactions between objects, which provide additional cues for high-level perception. However, there are multiple challenges that arise in 4D perception. The first challenge is that traditionally, a 3D CONVnet or 3D perception algorithm was not as competitive as 2D CONVnets. Also, the complexity of the 4D perception was prohibitively large. Thus, there have been only a handful of prior works in this domain. In this work, we used the proposed MINKOWSKI CONVnets for 3D perception, which resolved the first challenge. Second, we reduced the memory and computational complexity down by proposing the generalized convolution. The generalized convolution extends the convolution on sparse tensor to incorporate sparse tensor kernels. Here, we visualize the sparse tensor kernel along with the regular dense convolution kernel. On the left, we have the dense conventional kernel. Here it is 3x3 kernel, which requires 9 weights. However, as we increase the number of dimensions, the volume of the conventional kernel increases exponentially, which becomes already expensive for 4-dimensional space. Whereas if we use a sparse tensor for the convolution kernel, we can select an arbitrary element within a kernel to have parameters, which can drastically reduce the computation and memory required for convolution in high-dimensional space. To evaluate our network, we created a 4D semantic segmentation dataset from a synthetic dataset called Cynthia. And we used the same network architecture that we use for 3D semantic segmentation. But we use a sparse tensor kernel to reduce the computational complexity of the 4D convolution. Here's the prediction results of our 4D spatio-temporal CONVnet. Notice that the predictions are very accurate, as the 4D convolution is applied not just on the 3D space, but also along the temporal dimension, which smooths the prediction. There are many follow-up papers on this subject, and one paper, OQSEG, published in CVPR 2020, extended this semantic segmentation to panoptic segmentation and incorporated instance segmentation into one framework. It uses a sparse tensor 3D unit for accurate feature extraction and combined it with the supervoxel segmentation to achieve the state-of-the-art instance and semantic segmentation performance in one framework.
The next topic is 3D representation learning and registration. Within the representation learning, learning geometric features and representations is one of the most important areas. Specifically, 3D geometry features are vector representations of local or global 3D geometry. These features are used in 3D correspondences, registration, tracking, and scene flow. For example, on 3D scans from different perspectives, we want to find geometrically equivalent points. In geometric representation learning, we want to find a vector representation that is invariant to translation, rotation, scale, or occlusion. And many works proposed hand-designed 3D geometric features. Spin image, USC, shot, PFH, and EPIPH are hand-designed features that are based on binning one or more geometry properties. Recently, learning-based approaches gained popularity and achieved great performance boost in many tasks. Some use 3D convolutions on small 3D patches, but majority of them, like PointNet, PPF, FoldNet, PPF Fold, and CapsuleNet, are based on PointNet or MLP. However, all these feature extracts small 3D patches around interest points to map the local geometry within the patch to a vector representation. This limits the context a network can see, since the largest context is limited by the crop size. In addition, as the features are extracted from patches independently, all computations must start from scratch even when there's an overlap between patches, like the red boxes in the figure. Finally, many of these learned features require some low-level geometry as an input, which is sometimes expensive to compute. However, we can adopt the fully convolutional metric learning first proposed in the Universal Correspondence Network. The idea in the paper is that we do not have to extract patches to extract local features, and fully convolutional feature learning can share the intermediate feature maps and thus speed up the representation learning. We apply this fully convolutional metric learning to efficiently extract 3D geometry features. However, unlike the Universal Correspondence Network, where we learn features for all pixels, we use a sparse tensor for 3D representation and enforce the loss only on the valid surface, not on the empty region. We build our network using MINKOWSKI engine and combine the residual network with a unit to create this following architecture. However, in many cases, the majority of the pairs are negatives, and most of them are not helpful for feature learning process. There are many hard negative sampling methods, but we propose a new method called the hardest contrastive loss. The main motivation behind this loss is that we find the nearest neighbor in the feature space to find correspondences, but sometimes false attraction points can lead to poor correspondences since we are only sampling one nearest neighbor. In addition, the decision boundary is only defined by the hardest negatives. So instead, we sample the hardest negatives among all samples. On the left, we have the regular negative loss for contrastive loss, but by sampling the hardest negatives, like the equation on the right, we can substantially improve the performance. Visually, the hardest contrastive loss simply finds the most difficult negative pair among all negatives. We evaluate our method on the standard 3D match benchmark, which has been widely used for evaluating 3D representations. We use the feature match recall for the evaluation metric, which measures the number of image pairs that got at least 5% of the correspondences within a certain threshold correctly. Note that our method achieves a significant performance improvement compared with all learning-based methods. Specifically, at 10 centimeter distant threshold, our method achieves 95% recall, while the best prior work achieves below 70%. And here's the T-SNE visualization of our features. Note that the scans are randomly rotated in the scene, but we realign them to make it easier to understand. As you can see, the features from FCGF have similar colors on the corners, on chairs, and tables.
And here's the same visualization on the Kitty outdoor LiDAR scans of a street. Although the scans are taken from 10 meters apart, the colors at the corners and regions have the same color. We also measure the speed and accuracy of our method with all other 3D geometric features and plot the feature extraction speed on the x-axis and the feature match recall on the y-axis. Note that all variant features must sacrifice the speed to get good accuracy, and some hand design features have to trade off the accuracy for speed. But our feature, FCGF, outperformed all baselines while being the fastest and the most accurate. An interesting follow-up paper published from Facebook used this fully convolutional metric learning for self-supervised pre-training. First, you use this contrastive learning similar to the hardest contrastive loss, but they used these weights to fine-tune the network and used for many downstream tasks such as semantic segmentation, registration, and show that such pre-training can boost the performance significantly. The next topic that I will cover is the 3D registration. The 3D registration is a process of finding the transformation that aligns to scans, point clouds, or meshes. As many applications require such registration, many hand-designed and learning-based approaches have been proposed. These methods usually consist of several stages. The first one is feature extraction, followed by outlier filtering and transformation estimation. Even some end-to-end approaches have equivalent layers for these stages. Optionally, we can have the final fine-tuning stage as well. In this work, we propose a differentiable framework for end-to-end registration. For this, we propose six-dimensional convolutional neural network for outlier filtering and weighted procrastinus method for transformation estimation. And finally, robust gradient-based optimization method for fine-tuning the final registration. First, for feature extraction and matching, we use FCGF, fully convolutional geometric features. FCGF is currently the top-ranking algorithm for feature matching that is orders of magnitude faster and the most accurate. We densely extract FCGFs and use the nearest neighbor in the feature space for matching. However, like the visualization on the screen, not all correspondences are accurate, and we have to filter the outliers colored in red in this figure. In this work, we propose filtering the outliers with a six-dimensional convolutional network. To understand this, we first have to understand the geometric structure 3D correspondences form in the six-dimensional space. Let XYZ1 and XYZ2 to be a correspondence. A correct correspondence will satisfy the transformation equation like this, where R and T denote the ground truth rotation and translation respectively. If we reorganize the equation by concatenating the coordinates into a column vector, we have this matrix equation. And when we expand all the matrices, we have this following equation. Thus, we can decompose this into three equations, and each equation is a hyperplane equation in a six-dimensional space, which means that the solution must lie on the intersection of all these three hyperplanes. In other words, the inliers, or the correct correspondences, will lie on a three-dimensional subspace inside a six-dimensional space, whereas the outliers, or incorrect correspondences, will form noise outside this three-dimensional subspace. Thus, finding inliers is equivalent to finding this three-dimensional subspace, and finding this three-dimensional subspace is equivalent to foreground segmentation. Then, when algorithms are good at foreground segmentation, in 2D and 3D, convolutional neural networks are one of the most successful methods for semantic segmentation and foreground segmentation. And that is why we propose a six-dimensional convolutional neural network to segment the inner layers. We first extract a set of FCGF features and we find correspondences. Let XYZI and XYZI prime be a correspondence. Some correspondences are correct and others are incorrect, but there exists a pattern where correct correspondences will form in this space. Then these correspondences are stacked to create six-dimensional coordinates, and we simply use ones for all features to create a sparse tensor. Since we are not directly feeding the positional information to the network is translation invariant. Then we compute logit scores for all correspondences. Then we label each correspondence as either an inlier or outlier using the logit score. You can think of this process as foreground segmentation, where pixels in the input image are six-dimensional points generated from the correspondences. The next step in the pipeline is transformation estimation. The conventional method for estimating the 3D rigid transformation is the procrastinus analysis. Here, let XYZ1 and XYZ2 to be the correspondences. The Rx1 plus T defines the transformed XYZ1. If both correspondences and the rotation translation are accurate, it should be equal to XYZ2. Thus, L2 distance between Rx1 plus T and X2 XYZ2 gives us the error. The procrastinus analysis finds the R and T that minimize the squared error. However, it assumes that all correspondences are accurate and have the same importance or weight, which is not valid when we have noisy correspondences. Instead, we can use the importance or weight from the six-dimensional convolutional neural network to weight correspondences differently. And we propose weighted procrastinus analysis. In the paper, we show that it has a closed form solution and we can pass gradients through the weights. And this weighted procrastinus has a couple advantages. First, as we pass gradients through the weights, we can first train the network in an end-to-end fashion. And also, since the complexity is linear to the number of correspondences, which allows us to process many correspondences efficiently. Second, we can assign 0 to weights and can remove correspondences effectively, which is important when we have regions that have no overlap, like the highlighted regions in circles. Given the transformation estimate from the weighted procrastinus, the fine-tuning model further optimizes the pose for robust and accurate alignment. Specifically, we use a robust loss function such as Hubert loss instead of the L2 loss we use for weighted procrastinus and optimize the pose using gradient descent. Since we're optimizing a rotation matrix, it is important that we use a smooth, continuous representation to model the rotation matrix. Thus, we use the orthogonal representation proposed by Zhou et al., which we denoted as the function f. The function f takes 6 continuous real numbers and map these to a rotation matrix. Finally, we fine-tune these 6 continuous real numbers, denoted as A, along with the translation using gradient descent to find the final fine-tuned pose. In sum, the pipeline first starts with the feature extraction and matching using FCGF. Then weighted procrastinus converts these to a 60 pose, which we optimize further using a robust loss function. However, when the number of valid inliers falls below a certain threshold, we use a time-consuming but inaccurate registration method to guarantee that even when the network end-to-end registration fails, we have a fallback method that can provides an accurate registration. And this is the final algorithm for the deep global registration. Similar to FCGF, we trained our method on the 3D match benchmark. When we compare our method with the fast global registration and RENTEC, we achieve better alignment on small objects. For instance, on the chair on the left, and then the chair on the corner of the chair in the middle, as well as the cabinet. We also apply our method on a multi-way registration framework. This is the visualization of our multi-way registration result on the LiDAR RGBD dataset, Apartment C. Also, our method is agnostic to the input modality. So, we apply the deep global registration on the Kitty outdoor LiDAR scans. As you can see, the LiDAR scans are more sparser than the indoor scans. We trained the FCGF as well as the registration network on the Kitty scans and tested on the reserved test sequences. The yellow point cloud and the blue point cloud are LiDAR scans of an urban street taken 10 meters apart. Note that even when the point cloud is sparse, the deep global registration was able to successfully register these 2 point clouds. There are multiple concurrent works that share some ideas with our deep global registration. The first paper, Learning Multi-View 3D Point Cloud Registration, proposes an end-to-end registration on multiple scans simultaneously. Also, high-dimensional convolutional networks for geometric pattern recognition paper delves deeper into the patterns correspondences form and use a convolutional network to detect these patterns. In addition, it further extends this idea and uses the convolutional neural networks for general pattern recognition problems in high-dimensional spaces. Lastly, the Sparse Neighborhood Consensus Networks proposes a 4-dimensional convolutional network for image registration similar to the previous paper. The last topic that I will cover is 3D detection. Specifically, we're going to cover generative sparse detection networks for 3D single-shot object detection. Before we proceed, let's briefly cover 2 main branches of detection methods. The first major branch of 2D object detectors is the many-stage model, such as RCNN, where an algorithm generates a set of region proposals, which are then fed into the later stage for classification, bounding box regression, etc. In contrast, one-stage network generates the bounding boxes directly from the final feature map. In general, the single-stage or one-stage model tend to be faster and efficient, but at the cost of detection accuracy. Similar to 2D detection, there have been many works on this 3D object detection published last few years, and in particular, 3D semantic instance segmentation, and VoteNet proposed a single-shot and a multi-stage network respectively. The first work, 3D semantic instance segmentation, proposed using a dense 3D grid to represent the scene and applied a 3D convolutional neural network to detect objects. However, since it used a dense 3D grid, the resolution it can use was limited, and thus the detection accuracy was limited. The second work is VoteNet, which proposes an MLP-based 2-stage network that takes point samples from the surface to generate region proposals, which are then fed into a classification network for object detection. The computational complexity was significantly reduced since it only samples points from the surface, but the MLP has the low capacity, which led to lower detection performance. In this work, we propose a single-shot object detection network for high-resolution grid. For this, we adopt the sparse tensor representation to only capture the surface rather than the empty space to reduce the computational complexity and the memory required for detection. However, it introduces a new challenge for 3D detection that does not exist in the 2D image domain. Specifically, in 2D single-shot object detection, we can create bounding box anchors anywhere on the image, like the red boxes on the left image. But in commercial 3D scans, the surface observation does not cover the interior of the object, where the anchors or bounding boxes might lie. So, for a single-shot object detection, we have to generate a new set of coordinates that could cover the center of these bounding boxes. So, in this paper, we propose to adopt the recent generative pipelines to create bounding box anchors. In MINKOWSKI engine, by using the generalized convolution, we can create a new set of coordinates that are different from the existing coordinates to expand the set of new coordinates required for generative tasks. These generative tasks include 3D shape reconstruction, shape completion, or given a partial observation of the geometry, the network has to fill out the rest of the region or the entire shape. And this is particularly useful in scene completion tasks where we generate a complete scene from incomplete scans of a scene, which is quite common in robotics settings. Here, we visualize a typical generative process for 3D reconstruction. First, we feed an embedding that defines a class label as an input. Then the network expands it to the 3D dense grid. Then this dense tensor goes through a pruning process where we dynamically remove some voxels that might have low occupancy probability. Next, we subdivide the existing voxels into 8 subvoxels and repeat this pruning and upsampling process until we reach the target resolution. So, for object detection anchor generation, we use the similar process. We start from the input point cloud, and then we apply a series of deconvolution and pruning layers to generate a new set of coordinates that contain anchors that are semantically different from the input point cloud. Here's a visualization of two-dimensional example of this process. Let's say that we have a 4x4 grid, a convolution with strike 2 and deconvolution generate downsampled image, and then the original image resolution respectively. Similarly, in the sparse tensor, a strike to convolution and strike to deconvolution create downsampled and original point respectively. However, in generative convolution, we start from the downsampled point, but unlike the typical deconvolution, we create new pixels for each of the 2x2 grid. By repeating this process and adding skip connections, we can create a deep U-shaped network like this figure. In the end, by adopting the sparse tensor representation and removing the voxels at every upsampling stage, we can create a very high resolution point cloud and process the high resolution point cloud fully convolutionally without cropping. Quantitatively, our network was able to achieve 4 MAP improvement over the state-of-the-art method at 0.5 threshold. But since this is a single-stage network that does not have a post-processing stage, the improvement for the higher threshold was slightly lower. Also, When we compare the runtime of our single-shot method and the two-stage VoteNet, our method was on average 3.4 times faster. However, the improvement is even higher for small point clouds, since the sparse tensor representation converts irregular density point cloud to a probably uniform density point cloud. These are some visualizations of the ground truth bounding boxes and our network prediction on the Stanford dataset. At a first glance, our network was able to capture objects at a very high accuracy. However, it has a problem detecting thin objects like boards when the color is very similar to the wall. Also, sometimes it fuses multiple desks into one desk. We also ran our network on large-scale point clouds. We fed a full floor scan, which consists of 48 million points, into our network without downsampling or cropping. Even when we only trained our network on single room scans, not floors, since our network is fully convolutional, the network processed the entire floor accurately. Similarly, we also apply our network fully convolutionally on a few multi-story houses on the Gibson dataset without any pre-processing. Lastly, if you are interested in an outdoor object detection method for autonomous driving, the Centerpoint paper might be of interest to you. This method proposes combining a variation of a single-shot object detection methods with a convolutional neural network for sparse tensors for object detection and tracking on outdoor LiDAR point clouds. So, in conclusion, a sparse tensor is a powerful representation that is a direct extension of the discrete convolution in image and 3D space we are familiar with. And it also supports directional weights and is computationally efficient on high-dimensional data. And we briefly covered how we can use this as sparse tensor for segmentation, representation learning, registration, and detection, but are not limited to these applications. And to implement these ideas, we show how we can use the open source library called MINKOWSKI engine for this. And we are releasing the next version of the MINKOWSKI engine, 0.5. And we saw that for some networks, the speed up ranges from 3 to 8 times faster than the previous version. And that concludes my talk, and thank you all for your attention.